Welcome to Session 3 of Large Language Models, or LLMs. Last time we discovered that words can have geometry, that king minus man plus woman equals queen. Today, we go one step further. We're going to ask, what does it mean to read a sequence? Not just individual words, but words in order, one after another, carrying meaning from one to the next. Let me start with something simple, a sentence you'd give to a 5-year-old. The cat sat on the mat. Clear. Ordinary. The cat is doing the sitting. The mat is being sat on. Now read this. The mat sat on the cat. Saying 6 words. The mat is now the one doing the sitting, and the cat is being sat on. A very strange situation for a mat, but a completely different sentence. Same 6 words. Same word vectors. Same geometry from Session 2, but completely opposite meanings. Whatever we learned last time, beautiful and useful as it is, it's not enough. Something is missing. And what's missing is order. Let's make sure we understand exactly why this is a problem. Session 2 gave us beautiful word vectors. Take cat, sat, mat. Each one has a rich representation that captures something about what the word means. That's genuine progress. But every word has one fixed vector. The always has the same representation. Cat always has the same representation. Nothing changes, depending on where the word appears in the sentence or what surrounds it. To understand language, a machine needs to read it, left to right, in sequence. Not just know what the words mean in isolation, but process them in order, building up meaning as it goes. A bag of words model literally ignores order entirely. It sees only a set of word vectors and combines them. And the cat sat on the mat, and the mat sat on the cat look identical. That's the core problem we're solving today. So we need a new kind of architecture, something that reads sequences. A new architecture, the Recurrent Neural Network, does exactly that. It reads a sequence, one word at a time, and it keeps a running memory of what it's read so far. It seemed like exactly the right tool. Look at this one. The scientist who discovered the fossils was awarded the prize. By the time the RNN reaches was, it still has to remember scientist, a noun 5 words back. Can it? RNNs process sequences, but their training signal vanishes over distance. The beginning of a long sentence cannot reach the end. The RNN sees the words. It just can't learn from them when they're far apart. Before we see the problem, let's understand the idea. How do you even process a sequence? Imagine reading "The cat sat on the mat," one word at a time, keeping notes as you go. You read "the," and you note, this is probably the start of a sentence, probably a noun phrase coming. You read "cat," update your notes. Now you know we're talking about a cat. Sat, it's in the past tense. At each step, you update your notes with the new word, and you carry those notes forward to the next step. The notes connect one position to the next. That's a recurrent neural network. The notes are the hidden state, a vector that gets updated at every position. It's the machine's running summary of everything it's read so far. Every language model before 2017 worked some version of this way, some form of recurrence, step by step. For 20 years, this was the dominant approach to sequence modeling. The RNN cell is beautifully simple. One equation, repeated at every position in the sequence. HT equals tanh of WH times HT minus 1 plus WX times XT plus B. That's the whole thing. Everything you need to process a sequence is contained in this equation. XT is the word vector at position T, the embedding from Session 2. HT minus 1 is the hidden state carried forward from the previous step. These two things are combined to produce HT, the new hidden state. And here's the key, same weights at every position. The matrices WH and WX are shared across all positions. The network applies the same transformation to every word. What differs is the hidden state that comes in. The hidden state is the machine's running memory of the sentence so far. It's a fixed size vector, typically 128, 256, or 512 dimensions, that tries to compress everything the network has read. And here's one consequence. Position 1 and position 15 are processed with the same WH. Order is encoded only in the hidden state. The network has no other mechanism to track where it is in the sentence. Let's watch an RNN process our sentence. The is fed in. The network produces H1, its first hidden state. Right now, H1 encodes only that it's seen the. Not much to work with yet. Now, cat. The network takes H1 and xcat and produces H2. This hidden state now knows the cat, the start of a noun phrase. H1 fades to teal as H2 becomes the current state. Sat, past tense verb. H3 now carries noun phrase followed by past tense verb. The network is building a parse, implicitly, without being told what a parse is. The full sentence. The cat sat on the mat. 6 hidden states, 6 updates, the same pair of weight matrices applied 6 times. By the time we reach H6, the network has seen the entire sentence. Each HT carries the memory of everything the network has read so far. The architecture is elegant. It's just repeated application of the same cell. But here's the thing. By H6, the entire sentence is squeezed into a single fixed-size vector. 6 words or 600 words, all forced into the same 256-dimensional space. That squeezing gives the RNN its power. It's also exactly where it breaks. So what is actually living in the hidden state? What has the RNN learned to encode? Short-term context, what was just said, the grammatical role of recent words. The network knows sat is a verb because cat was a noun and this is the right position for a verb. Subject tracking, who is doing what? The network maintains some representation of the subject of the sentence so it can apply the right verb. Tense and mood. Sat puts the entire sentence in the past tense. That tense signal needs to persist through the rest of the sentence. A positional signal, some implicit sense of how far through the sequence we are. This is weak and implicit, but it's there. Understanding the architecture is one thing. Training it is where the real problem begins. To train an RNN, we need gradients. We need to know how to adjust WH and WX to make the network's predictions better. Gradients tell us the direction to update. We unroll the network through time, just like we visualized on the previous slide, and we backpropagate through each step. This is called backpropagation through time, or BPTT. To blame the word at position t equals 1 for an error that appears at t equals 6, the gradient has to travel backwards through all 5 steps between them. It starts at the output and flows left. At each step, the gradient is multiplied by WH. 5 steps means 5 multiplications. That's where the trouble starts. For a sentence of 50 words, 49 matrix multiplications, 1 for every step back from the last word to the first. The gradient doesn't just shrink gradually, it disappears. Let me show you what this looks like. Watch the gradient shrink as it flows backward through time. We start at the output, position 6. Here's the gradient at the output, position t equals 6. We set this to 1.0. This is where training information originates. 1 step back, t equals 5. Already the gradient has fallen to about half its size. After 1 multiplication by WH, just over half the signal survives. T equals 4. Another multiplication. The gradient is now about a quarter of its original size. T equals 3. About an eighth. We're 3 steps from the output and already losing the signal badly. T equals 2. About 7%. We're 2 steps from the beginning and the gradient is nearly invisible. And here's t equals 1, the very first word of the sentence. The gradient is down to about 4% of what it started as. For the word at position 1, for the in our example, or for whatever word begins a 50-word sentence, the training signal is effectively 0. By t equals 1, the gradient is near 0. The earliest words no longer influence training. They're invisible. They might as well not exist. Why does this happen? Let's understand the mathematics. It's actually quite simple. At each step, the gradient is multiplied by WH, the recurrent weight matrix. That's not an approximation. That's exactly how the chain rule works in BPTT. If the overall scale of WH, loosely its size, is less than 1, and with standard initialization it usually is, Then each multiplication shrinks the gradient. 5 multiplications, down to 0.5 to the 5th power, about 3%, matching the chart you just saw. 49 multiplications, the 50-word case, essentially 0. And if it's greater than 1, the gradient explodes instead, growing exponentially until training becomes numerically unstable. You can clip exploding gradients as a hack, but you can't fix the vanishing case so easily. The RNN cannot learn long-range dependencies, not because of a bug, but because of mathematics. Bengio and colleagues proved this formally in 1994. The architecture is fundamentally broken for long sequences. What does this mean when you actually try to build something with RNNs? Short sequences, 5 to 10 tokens. RNNs work well. The gradient reaches the beginning. You can do part-of-speech tagging, named entity recognition on short spans, simple classification tasks. Medium sequences, 20 to 30 tokens. Some information survives, but the beginning of a sentence is blurry. The network has a faded, imprecise memory of what it read first. Long sequences, 50 or more tokens. The earliest words are effectively invisible to the gradient. The model can't learn from them. Subject-verb agreement across a long clause? Largely impossible. Real language doesn't cooperate. Sentences routinely span 30, 50, 100 words. News articles, legal documents, academic papers. The sequences that matter most are exactly the ones RNNs struggle with. In practice, RNNs were usable up to about 20 tokens. Beyond that required tricks, workarounds, and workarounds on top of workarounds. The architecture was fighting its own mathematics at every step. Let's place this in time. The vanishing gradient wasn't a surprise. Researchers knew about it. The question was, how to fix it? 1986. Rumelhart, Hinton, and Williams derive backpropagation through time. The algorithm works, and it's elegant. And it already contains the vanishing gradient, though it will take years to see that. 1990. Jeffrey Ellman builds simple recurrent networks and shows they can learn sequential patterns. Short ones, but real ones. 1994. Yoshua Bengio and colleagues prove it formally. Vanishing gradients are not a quirk of implementation. They are an inherent consequence of the architecture. So this isn't something a better implementation will fix. 1997. Sepp Hochreiter and Jürgen Schmidhuber published the long short-term memory network. They solved the problem, for medium-range dependencies at least. This is the resolution. 2015. Bidirectional LSTMs, running the sequence both forwards and backwards simultaneously, become the standard for tasks like named entity recognition and machine translation. But between 2014 and 2017, a different idea takes shape. Bodenau's attention mechanism arrives in 2014 as a preprint, published the following year. By 2017, Vaswani and colleagues publish Attention is All You Need, and the transformer makes recurrence obsolete. So how did Hochreiter and Schmidhuber solve the vanishing gradient problem? The answer is elegant. What if we added a second kind of memory? One that doesn't go through the same multiplication at every step. One that can persist unchanged across many positions? The LSTM adds a cell state CT, a separate line of information that runs alongside the hidden state. Think of it as a highway that runs parallel to the main road. Information can travel along it without being filtered at every exit. 3 gates control what information enters the cell state, what leaves it, and what gets erased. Each gate is a small sigmoid network that outputs values between 0 and 1, open or closed, or anywhere in between. And here's the critical insight. Addition doesn't shrink. The RNN multiplies the gradient through WH at every step. But the LSTM cell state propagates through additions, and the gradient of an addition is just 1. Let's build the LSTM cell gate by gate. Step 1. The cell state highway. This is the key innovation. CT-1 comes in from the left, and CT goes out to the right, along a nearly unobstructed path. Information can travel along this highway with minimal transformation. The gradient flows backwards along the same path, almost undimmed. Step 2. The forget gate. A sigmoid node labeled sigma takes HT-1 and XT as inputs and produces a value between 0 and 1 for every dimension of the cell state. Near 0, erase this memory. Near 1, keep it. This is multiplied into the cell state, selectively erasing what's no longer needed. Step 3. The input gate. Two operations together. A sigmoid, how much to write, multiplied by a tanh, what to write. The result is added to the cell state. New information flows in only where the gate decides it should. Step 4. The output gate. A final sigmoid decides which parts of the cell state to expose to the outside world. That filtered signal passes through a tanh and becomes HT, the hidden state that the next cell, or the final output, will see. 3 gates, 1 cell state. The entire cell, 4 weight matrices, 3 gates, 2 outputs, HT and CT, is learned end-to-end. The network learns when to remember and when to forget. The cell state CT can carry information unchanged across hundreds of steps because it passes through additions, not multiplications. That's what breaks the vanishing gradient. Let's be precise about what each gate is actually computing. The forget gate, FT equals sigma of WF times HT minus 1 and XT plus BF. The same combine and transform idea as the RNN cell, just written as one matrix over the 2 inputs stacked together instead of 2 separate matrices. Multiplied into CT minus 1. Values near 0 erase that dimension of memory. Values near 1 preserve it. If the model just read a period at the end of a sentence, it should forget the current subject. The sentence is over. The input gate, IT times G tilde T, added to the cell state. IT, a sigmoid, controls how much to write. G tilde T, a tanh, is the candidate content. Together they decide what new information to store. If a new subject appears, store it. The output gate, OT equals sigma of WO times HT minus 1 and XT plus BO, filters tanh of CT to produce HT. Not all of the cell state needs to be visible to the next layer, only what's relevant for the current prediction. The LSTM works, but it's not the only answer. Let's see how far you can simplify it and still keep the trick. What if we simplified the LSTM's idea even further? 1 memory line instead of 2. The GRU, gated recurrent unit, drops the separate cell state entirely and merges the forget and input gates into one update gate. Cho and colleagues, 2014. 2 gates instead of 3. A reset gate decides how much of the past to use when computing a fresh candidate. An update gate decides how much of that past to keep versus overwrite with the candidate. Same highway trek as the LSTM. Hold the update gate near 0, and the old hidden state passes through almost unchanged. Let's build the GRU cell the same way we built the LSTM, gate by gate. Step 1. The hidden state highway. Notice there's only 1 line here, not 2. HT minus 1 comes in from the left, and HT goes out to the right, and that same HT minus 1 is also what we feed in as input below. No second parallel cell state to keep track of. Step 2. The reset gate. A sigmoid, red, reads HT minus 1 and XT and decides how much of the past hidden state to let through into the candidate computation. Near 0, ignore the past almost entirely. Near 1, use all of it. Step 3. 2 things at once. The candidate, a tan, computes a fresh guess at what HT could be using the reset gated past and the current input. And separately, the update gate gold, another sigmoid, decides how much of that fresh guess to actually use. Step 4. The blend. Right on the highway itself, gold, 1 minus the update gate times the old hidden state, plus the update gate times the candidate. That's HT. No separate output gate, no separate readout. The blend result is the highway's next value. 2 gates, 1 state. No separate cell state to maintain, no separate output gate to filter through. The whole cell is 2 sigmoids and a tanh, wired together. When the update gate sits near 0, HT-1 passes through the blend almost unchanged. That's the GRU's own version of the LSTM's highway, built with 1 gate fewer. Let's compare all 3 architectures, head to head. The RNN has 1 memory path, the hidden state, and the gradient passes through WH at every step. The LSTM has 2 memory paths, hidden state plus cell state, and gradients can use the cell highway, which is nearly linear. The GRU keeps just 1 memory path like the RNN, but protects it the same way the LSTM protects its highway. When the update gate is near zero, the old state survives almost untouched. The practical difference: RNNs lose long-range information beyond about 20 tokens. LSTMs and GRUs are both reliable, up to 50 to 100 tokens, sometimes more. And the GRU gets there with fewer parameters. In practice, LSTMs and GRUs were both defaults for NLP from 1997 to 2017, 20 years. Speech recognition, machine translation, language modeling, question answering, both architectures were everywhere. And teams often reached for the GRU first when training speed mattered. Then attention arrived, and the landscape shifted entirely. One of the most useful things about the RNN family is its flexibility in input-output shape. Many to one. A full sequence in, a single output. This is what you use for sentiment analysis. Read the entire review, output a single score. Or for document classification, spam detection, intent recognition. Many to many. Multiple inputs, multiple outputs. This is machine translation. Read the French sentence word by word, output the English translation word by word. The input and output sequences can be different lengths. One to many. A single input, perhaps an image embedding, a seed word or a prompt, generates a sequence of outputs. Text generation, image captioning, music generation. One architecture, many problems. The recurrent cell is identical in each case. What changes is how you feed inputs and read outputs. Each task type requires different training data, input-output pairs, where the output has the right shape. But the underlying mechanism is the same cell, the same hidden state, the same equations. LSTMs are a genuine improvement, but they didn't fully solve the problem. Let's be honest about their limitations. Very long sequences, 100 tokens or more, and even the cell state struggles. Subject-verb agreement across a long relative clause, pronoun resolution across a paragraph, these still break down. The gradient highway is good, but it's not infinite. Parallel computation is impossible. Step T requires the output of step T-1. You can't process position 5 until you've processed positions 1 through 4. That means training on GPUs, which are built for parallel computation, is fundamentally inefficient. Training a large LSTM is slow. Global context doesn't exist. At position 80, the model has only a filtered, compressed memory of what it read at position 1. Nothing reads the whole sentence at once and lets every word talk to every other word directly. The fixed bottleneck. Think back to the translation example. We drew that as one box for simplicity, but a real translation system splits it into two RNNs. One reads the French sentence, a second writes the English one. Call the first the encoder and the second the decoder. The entire source sentence must be compressed into a single vector, HT, before the decoder starts writing a single word. If the sentence is long, information is lost. This bottleneck is unavoidable in that encoder-decoder setup. And scale. When researchers started training much larger models on much more data, the transformer scaled beautifully. Performance kept improving. LSTMs didn't. The architecture had hit its ceiling. We've improved the situation. LSTMs can handle 50 to 100 tokens. That's real progress compared to basic RNNs. But the fundamental constraint remains. We process sequences sequentially, one step at a time. What if we threw out recurrence entirely? What if, instead of reading word by word and accumulating a hidden state, every word could look directly at every other word simultaneously, in parallel, with no distance penalty? That is the attention mechanism, and it changes everything. Session 4. Let's place ourselves in the 14-session story. Sessions 1 and 2. Motivation and representation. We know why language is hard and how to represent words as vectors. Session 3. Sequences and memory. We know how to process word sequences, and we know exactly why RNNs fail. We've met LSTMs and understand what they fix and what they don't. The rest of the journey. Sessions 4 and 5 introduce attention and the transformer, the architecture that powers every large language model in use today. Then BERT, GPT, scaling, alignment, efficiency, the full picture of modern AI. Today we introduced the sequence problem and partially solved it. Next time, we break the distance limit entirely. In today's 2-hour lab, you'll build this from the ground up. no black boxes. Part 1. Implement a character-level RNN in PyTorch and train it on a small text corpus. Shakespeare, a fairy tale, anything short. Predict the next character, one step at a time. Part 2. Sample from your trained RNN. Look at what it generates early in training, random noise, and late in training, something that looks suspiciously like language. The improvement is visible and satisfying. Part 3. Swap the RNN cell for an LSTM cell. Same training loop, same data, just one architectural change. Compare the outputs. Can you see the LSTM handling longer patterns? The challenge. Construct a sentence where the correct verb form depends on a noun that appears 30 tokens earlier. Feed it to both models. Measure how often the RNN fails and the LSTM succeeds. You'll have your own empirical proof of the vanishing gradient problem.